This lecture is about mixture model estimation. In this lecture, we're going to continue discussing probabilistic topic models. In particular, we're going to talk about how to estimate the parameters of a mixture model. So let's first look at our motivation for using a mixture model. And we hope to factor out the background words from the topic word distribution. So the idea is to assume that the text data actually contain two kinds of words. One kind is from the background here. So the, is, or we, etc. And the other kind is from our topic word distribution that we're interested in. So in order to solve this problem of factoring out background words, we can set up our mixture model as follows. We're going to assume that we already know the parameters of all the values for all the parameters in the mixture model except for the word distribution of theta sub d, which is our target. So this is a case of customizing a probabilistic model so that we embedded the unknown variables that we are interested in, but we're going to simplify other things. We're going to assume we have knowledge about others. And this is a powerful way of customizing a model for a particular need. Now you can imagine we could have assumed that we also don't know the background word distribution. But in this case, our goal is to factor out precisely those high probability background words. So we assume the background model is already fixed. And the problem here is how can we adjust theta sub d in order to maximize the probability of the observed document here. And we assume all the other parameters are known. Now, although we designed the model heuristically to try to factor out these background words, it's unclear whether if we use maximum likelihood estimator, we will actually end up having a word distribution where the common words like the will be indeed having smaller probabilities than before. So now, in this case, it turns out that the answer is yes. And when we set up the probabilistic model in this way, when we use maximum likelihood estimator, we will end up having a word distribution that where the common words will be factored out by the use of the background distribution. So to understand why this is so, it's useful to examine the behavior of a mixture model. So we're going to look at a very, very simple case in order to understand some interesting behaviors of a mixture model. The observed patterns here actually are generalizable to mixture model in general, but it's much easier to understand this behavior when we use a very simple case like what we're seeing here. So specifically, in this case, let's assume that the probability of choosing each of the two models is exactly the same. So we're going to flip a fair coin to decide which model to use. Furthermore, we are going to assume there are precisely two words, the and the text. Obviously, this is a very naive oversimplification of the actual text. But again, it's useful to examine the behavior in such a special case. So we further assume that the background model gives probability of 0.9 to the word the and text 0.1. Now let's also assume that our data is extremely simple. The document has just two words, text and the. So now let's write down the likelihood function in such a case. First, what's the probability of text and what's the probability of the? I hope by this point you will be able to write it down. So the probability of text is basically the sum over two cases where each case corresponds to each of the word distribution, and it accounts for the two ways of generating text. And inside each case, we have the probability of choosing the model, which is 0.5, multiplied by the probability of observing text from that model. Similarly, the would have a probability of the same form, just with different exact probabilities. So naturally, our likelihood function is just the product of the two. So it's very easy to see that. once you understand what's the probability of each word, which is also why it's so important to understand what's exactly the probability of observing each word from such a mixture model. Now, the interesting question now is how can we then optimize this likelihood? Well, you will notice that there are only two variables. They are precisely the two probabilities of the two words, text and the, given by theta sub d. And this is because we have assumed that all the other parameters are known. So now the question is a very simple algebra question, right? So we have a simple expression with two variables, and we hope to choose the values of these two variables to maximize this function. And it's exercise that we have seen in some simple algebra problems, right? And note that the two probabilities must sum to 1. So there's some constraint. If there were no constraint, of course, we would set both probabilities to their maximum value, which would be 1 to maximize this. But we can't do that because text and the must sum to 1. We can't give both a probability of 1. So now the question is, how should we allocate the probability mass between the two words? What do you think? Now, it would be useful to look at this formula for a moment and to see what intuitively would we do in order to set these probabilities to maximize the value of this function. Okay, if we look into this further, then we'll see some interesting behavior of the two component models in that they will be collaborating to maximize the probability of the observed data, which is dictated by the maximum likelihood estimator. But they are also competing in some way, and in particular, they will be competing on the words. And they will tend to bet high probabilities on different words to avoid this competition in some sense, or to gain advantage in this competition. So again, looking at this objective function, and we have a constraint on the two probabilities. Now, if you look at the formula intuitively, you might feel that you want to set the probability of text to be somewhat larger than the. And this intuition can be well supported by a mathematical fact, which is when the sum of two variables is a constant, then the product of them reaches maximum when they are equal. And this is a fact that we know from algebra. Now, if we plug that in, it would mean that we have to make the two probabilities equal. And when we make them equal, and then if we consider the constraint, we can easily solve this problem. And the solution is the probability of text would be 0.9, and the probability of the is 0.1. And as you can see, indeed, the probability of text is now much larger than probability of the. And this is not the case when we have just one distribution. And this is clearly because of the use of the background model, which assigned a very high probability to the and low probability to text. And if you look at the equation, you will see obviously some interaction of the two distributions here. Right. In particular, you will see in order to make them equal, and then the probability assigned by theta sub d must be higher for a word that has a smaller probability given by the background. Right? And this is obvious from examining this equation, because the background part is weak for text. It's small. So in order to compensate for that, we must make the probability of text given by theta sub d somewhat larger so that the two sides can be balanced. So this is in fact a very general behavior of this mixture model. And that is, if one distribution assigns a high probability to one word than another, then the other distribution would tend to do the opposite. Basically, it would discourage other distributions to do the same. And this is to balance them out so that we can account for all kinds of words. And this also means that by using a background model that is fixed to assign high probabilities to background words, we can indeed encourage the unknown topic word distribution to assign smaller probabilities for such common words. Instead, put more probability mass on the content words that cannot be explained well by the background model, meaning that they have a very small probability from the background model, like text here.